Ever wondered about the difference between electric charge and current? Yeah, you are definitely not alone. It's one of those ideas at the very heart of electronics that can seem a little mysterious. But stick with me and you'll see it's actually incredibly simple.
So, here's our game plan. We're going to start with the basics, then visualize how it all flows. We'll look at the kind of mind-boggling numbers involved, see why this actually matters for your tech, and then wrap it all up with a few top questions. Let's dive in.
All right, first things first. Let's really nail down the fundamental definitions. This is the foundation for, well, everything else. Once you get this part, everything else just clicks into place. So let's just dive right in and tackle the big question head on. What really separates these two core concepts? Okay, so electric charge, which we usually write as a Q, is a basic property of matter. You know, just like mass. You can think of it as a static thing, the total amount of electricity that an object is just holding, and we measure this in a unit called coulombs.
And then you have electric current. We call it I. And that's just what happens when all that charge starts to move. It's not about how much stuff there is, it's about the rate of flow, how fast that stuff is moving past a certain point. And that's what we measure in amperes or amps.
You know, the absolute best way to get this is the river analogy. Imagine a huge river. All the water in that entire river system, that's your charge. But how fast that water is flowing past you, the amount of water rushing by every second, that is the current. See? One is the stuff, and the other is the speed of the stuff.
Okay, so we've got the concept, right? Now let's see how the math behind it works. And don't worry, I promise this is way simpler than it might look.
Whoa, okay. I know this looks like a lot of formulas. And yeah, some of this is for some pretty advanced physics. But for us, we just need to look at that simple green triangle. It's a great little memory tool. You see charge, Q, on top, with current, I, and time, T, on the bottom. It's a perfect little picture of the main relationship we care about. Current is just charge divided by time.
So, let's really lock in that formula. I equals Q over T. What this really tells us is the definition of an ampere itself. 1 amp literally means 1 coulomb of charge is flowing past a point every single second. That's it. That's the pulse of electricity.
All right, let's bring this out of the world of formulas and into the real world. We talk about amps and coulombs, but what's actually happening with the tiny little particles that make it all work? Well, the scale is genuinely shocking.
So yeah, think about it for a second. We know an electron's charge is teeny tiny. So for just 1 amp of current, which is super common, how many of these electrons do you think have to be zipping past a point every second? Go on, take a wild guess.
You ready for this? The answer is 6.24 times 10 to the power of 18. Just let that number hang in the air for a second. It's almost impossible to really picture.
If you're wondering what to even call that number, that's 6.24 quintillion. So that 1 amp charger for your phone, it means that every single second, more than 6 quintillion electrons are literally marching through that little cable. It's this huge, invisible army of particles.
And look, this isn't just some crazy piece of trivia. Knowing this connection between the amount of charge and how fast it's moving is absolutely critical. Let's see how this theory connects directly to the tech you use every single day. So why does this matter so much? Well, for starters, safety. You know that current rating on your phone charger? That's telling you the maximum flow that cable can safely handle. If you try to push too much current through a cheap cable, it's like trying to force a whole river through a tiny garden hose. It's going to get hot and it can get dangerous. Seriously, this concept is the bedrock of pretty much every electronic circuit ever made.
All right, to really make sure this all sticks, let's just quickly run through a couple of the most common questions people have about all this.
Okay, let's boil everything we've talked about down to the most important question and make sure it's unforgettable.
And here's the simplest possible answer. Just remember this. Charge is the stuff. Current is how fast the stuff is moving. That's
Okay, here's another fantastic question that really gets to the heart of it. Is it possible to have the stuff if it's not flowing?
Oh, for sure. 100%. Just think about static electricity, right? When you rub a balloon on your hair, you're building up electric charge, but it's just sitting there. You have charge, but you have zero current. The second that charge gets a path to move,
Like when you touch a doorknob, that's when you get a current.
By the way, all the great info in this explainer is based on some fantastic content over at electronicsed.com. If you really want to go deeper on this stuff, you should definitely check them out. They do a great job of making things clear.
So I'll just leave you with this one last thought. The next time you plug your phone in, or, just flip on a light switch, just picture it for a second. That enormous, invisible army of quintillions of electrons marching in unison through that wire every single second just to power your world. It's the tiny charges in motion that bring everything to life. Thanks for joining me on The Explainer.